Hello, this is the very first lecture of the course on nonlinear polymer rheology based on the book published by Wiley. And I'm going to cover some background, some introduction on this course. And as we start to figuring out that, the first class always, despite the homework you've done, let's see, so you always have, okay, so what is being recorded will be what's on the display. And I'm trying to open up various documents. So first thing first, as you may not know, this book is what I will base our courses on, is free available in its soft copy through our library. The library will have a link to Wiley, and it's all for free. And as for the convenience of you, which is, it turns out it's very convenient. It was so enjoyable that you just flip to the different pages. Instead of me drawing all the curves, I just show you the different formula, different figures. And so it would be nice for you to have a hard copy, which I do have. So I'm showing you a copy of it. Today we will not use much of this book, so it's okay. But I'm showing you a copy of this that I have enough copies for each of you to borrow until the course finishes. This was 3 years ago when the book has yet to be in print form. I told the publisher I want to start to teach, and they were kind enough to provide all the more than 20 copies of this made it for me. Although the only thing is it was before proof corrections, so there were still lots of typos. But page by page is identical to the book. So the typos are certainly correctable. It's very usable. So my intent was we have about 10 people. I would bring 10 copies next time to you. Clear that part? So you will, and we will probably be able to save lots of time. Instead of writing everything down, I would just say, oh, turn to page 33, and then we'll take a look at there. I know that's not very good for the recording part. I just realized that. But for this, I know this is a very special time, and where's a piece of paper? I was told that you guys need to fix the seats and each time use the same seats. I realize I don't have the paper. So basically, I will at some point, perhaps at the end of lecture, for you to write down your name and corresponding seats, and also write down your name so that I have a record. You will have a book of this. Okay. No idea how. I assume it's being recorded. I don't see a highlighted frame. But let's get started. There's so much to talk about. As I said, for this to be interesting, for this class to be interesting, I hope I can get a lot of interactions with you, because quite a bit of that is not necessarily technical. And it means that you need to make a lot of judgment on them. In any case, I already made I don't, you guys will be jealous. I don't think I can match, this is meant to be a joke. I don't think I can match the energy I had when I first taught it in 2017. And the joke was, the only reason I'm so excited talking about is because the content has not been accepted. Large, totally. And you will see in many cases, the difficulties of doing science and the challenge to find the right approach to do the right science. And certainly depend on what kind of science. Today, I can assure you I know how to do polymer physics type of science. If you ask me to do biology, it might require a slightly different approach. So this is already getting interesting in that sense. But for what we do, for what I do for 30 years, I know what's most effective. So I will start with many pieces of information. So let me first start with a laugh at myself. So I was teaching at the Case Western for 11 years until 2000. And I was hired to teach polymer physics, and gradually it seems polymer rheology is a course graduate students should know. So I started to pick up that subject and start to teach by self-learning. So I want to, there will be many things to, I want to indicate how I was killing my time. I really mean it, meaning fulfill a 3-credit course by teaching out of nothing. I wish to say that there's very little. It's largely empty, what I was doing some 25 years ago. Okay? So, man, there was a joke that quickly, I didn't realize that even at that time. One of my colleagues complained that, oh my God, to teach student tensor and all this is so hard. And I quickly replied to my colleague, I said, gee, you know, one day I'm going to write a book called Rheology Without Tensors. This book is largely a book without tensor. And I noticed right away, even before we had any revolutionary ideas or discoveries, rather, that rheology is hitting a dead wall, discouraging all the people from entering, because you open their book, the first 3 chapters are on tensor analysis. Is that so? Is that the essence of rheology? Do we need it? When do we need it? Okay? So the joke meant to be serious when I had it, because I appreciate it, even without knowing anything new at that time, or without knowing that polymer rheology has something to be discovered. I already knew that, why should we keep talking about tensors? Well, which I do, okay? And a little bit of casual discussion of what we see. And certainly, this is all experimental information about how to make measurements, fine. And kill a little bit time on just running out of time, you know, kill a little bit time on saying a little bit of the modeling beyond what is Newtonian. We'll get to there soon. And kill a little bit more time about being a little bit mathematical about what are certainly not so useful exercise about how to describe rheology. And then, of course, on the theory part, it's basically a little bit of what was known at that time. And the reason today this book is not a textbook yet, I wrote it as if it is a textbook, and I believe it will become. But the reason it is not is the challenge that you will come to appreciate. I wish I brought a demonstration, but the appreciation is this. Any material, in our case, is polymers. And in our case, we are studying rheology of polymers. Traditionally, it is, if you spoke to anyone, it is almost without mistake that they meant you to speak about your dear polymer. We have several hundred billion pounds of them, right? Large amount each year being processed. And when they are processed above their glassy state, so it's no longer a solid, above their melting point, so they are no longer semi-crystalline, and it's something like a honey piece of that sort. And polymer rheology supposedly deal with that matter in that state, about Tg, about Tm, where the polymers are no different than, well, I know I should have a copy for you already. I could, basically, the polymers are just a bunch of chains randomly packed like this in its coiled form. And fine. When I ask you to visualize this, they are in nanometer scales, right? Each chain, I think everyone is aware of molecules are quite small in the nanometer scales. And very few tools can allow me to visualize each chain, let alone follow this chain when the chain moves around. In this liquid state, they will move around. And that's going to be an important part, how fast they move around. That's something we're guessing it's in that form. And then everything else you do processing, it's all microscopic. You know, I will definitely remember to bring something next time to demonstrate this. But basically, imagine this the way this bottle is made, right? It's obviously microscopic, millimeter scales. So you can see whatever you claim to understand about how this honey-like thing come into the shape of this that you can observe is on millimeter scales, whereas whatever that it resists or not resists to come to this shape depend on how molecules respond to it. And that's 6th order magnitude gap. Nanometer to millimeter is a 6th order magnitude gap. And the lack of any direct visualization between how nanometer scale stuff are responsible for what we see in millimeter scale is the lack of it is the challenge, is the reason this book is not textbook yet. But we are scientists, right? So we use reason, we use logic, we use induction method. Sometimes we even use deduction method. This is a part of scientific method that I'm teaching in the other course. But there are philosophical issues coming in. But in general, I can say that, so in any case, this is a few things of what I was able to say and kill time. If you're not convinced that what we're dealing with today is different, here is a course being currently offered, well, for example, 3 years ago, in polymer engineering. And should I read it? So the introduction, stress strain, continuum mechanics, measurements. So basically, the book that was used is a book on rheology, a rheological method. There was very little discussion about the polymer science behind it. So if you are not bored with it, just for completeness, the subject we're dealing with, I want to get you realizing that we're dealing with something massive. The subject we're dealing with, something like 30 books have been written on. Okay? I highlighted more than half of the book that are not only just looking at rheology in general. In other words, rheology, I repeat this word many times and you will hear it. Rheology supposedly is a science that deals with how matter deforms. So that material doesn't have to be polymeric. So in that sense, rheology has some general principles, including the way you make measurement is general as well, subject to whatever is your rheological property. Some instrument may work, some may not. So in any case, this is the available books. And well, shouldn't we have reached the end of it? Some books are as recent as just 10 years ago. So what are we doing here, right? So let me just, it's my wish. I don't know. Of course, this is not the case. The best result we would have been that you have taken polymer rheology from somebody else already. I mean, and then come to mine, and you will have the contrast. In absence of that, I could only indicate what is available in the open literature up until very recently. So I was not trained in rheology, which is a blast, okay? So I teach myself by reading books such as Bird's book. Half of them is verbal description, another more than half is all mathematical. If this is recorded, I probably shouldn't say anything very negative about any of these books. You will be able to, you will be the judge how useful what can you learn from it. And this is, of course, is a very useful book, very popular, because it describes just how to make a measurement, all kinds of different things. But again, they start with sort of a traditional. I remember Professor Markowsko in his introduction was mumbling in his preface, should I talk about tensor and all this? And then he said, let's still do it that way. So this is a book heavily popular, not on the polymer physics side of rheology, but just rheology in general. And this is another book where I can be a little bit critical, perhaps, and you will find that to be acceptable. You will soon find that to be acceptable. Look at this book, for example. I just highlighted a few places where the word flow was used. I want to call your attention that the use of that word is largely problematic. Moreover, I would say in the literature, there will be 10,000 times the word flow is used inappropriately, incorrectly. So this will almost become the central point of our subject. Moving on, as I said, I was killing time. When I say killing time, I mean, I like to verbalize a lot, so let me just verbalize this. The rheology is, I already said, it's a science about deformation of matter. But really, there are two dichotomy. There are two sides of rheology. It is either as a characterization tool, and that's what most people are commonly aware of, the subject. It's a characterization tool. It allows you to learn something about so-called viscoelasticity. We'll get to that somewhat. But that's hardly what rheology is about. The characterization as rheology typically deal with, you'll hear this a million times, deal with so-called linear response. We'll come back to what it means many times. But basically dealing with a case where the material is left there very little agitated, very little touched, very little deformed. We will be more precise much later. But really the mission of rheology, the core part of rheology, is not the characterization tool. Just like, for example, NMR, that is really a characterization tool. It's built on certain physical principles, but it's just a tool. It cannot expand itself to become a science. Rheology, the core part of it, is the science of it, not the part as the tool. In other words, rheology itself is a branch of polymer physics. It's a part of a science. When I say that, I mean the following. That, for example, this book by a very brilliant rheologist, Grassley, who passed away, though, however, is that the science which has to do with nonlinear, has to do with I beat it very badly and watch what happens. Well, why you beat it very badly? when you try to do processing, you want to process this as fast as you can, okay? Which means if there's a nozzle, you want to squeeze your polymer out of that nozzle as fast as you possibly can so that you can make 1,000 of this in an hour instead of 10 of them. Get it? So this is, in that sense, we're beating it, okay? We're trying to subject our polymer to something as fast as possible. And we'll come back to what I mean by fast in detail, meaning deforming very fast. When things are being subject to fast deformation, I'll use this term a million times, so I don't need to be very careful at this point, but basically I explained it. When we don't have time, we need fast. Then we encounter a whole set of phenomena or a new world that is so hard to understand because of the 6th order magnitude gap. When I subject something to that fast, what happened to those molecules at nanometer scales? And apparently they do something, produce something that's beyond comprehension, and that's how we are trying to figure out. And when you are dealing with this nonlinear part, then it turns out, until even just 10 years ago, there's very little we know. Or there's very little I can be so confident and talk about. Lastly, this is another book. It was a re-edition, where I want to indicate that the nonlinear part is again rather small, limited to a very small part of the discussion, rather small. And we'll get to the theory part that they are advocating for. So here comes the essence. I mean, if you understand this essence, we're done with this course in some sense. But of course, you won't be able to tell what I mean by this yet. So, but I do want to point it out. Perhaps a little too early, but it's okay. In this book, very recent, and it was recently republished again. I had an e-copy, so I could count. There were words called yield used 48 times. And you have no clue what I mean by saying none of them means what we mean. So yield in English means produce, right? If I do this, I yield this result. I produce this result. Okay? Well, I don't know. Sometimes people read much faster than anything else. But basically, in our book, I jokingly called it's a book without tensor, but not without data. In other words, to speak about nonlinear rheology is so hard unless you have enough data. So this is a book full of data. There are 360 figures, something around that. And we used the word yield or yielding hundreds of times. And the very notion of this word is controversial. The mainstream rheologists in the community today still find it unfamiliar, if not objectionable, concerning this concept of yield. So, having said that, I think I get you curious enough to want to know what is all this about. What do we mean by yield? Why that yield carries a particular meaning? Well, let me not put you in suspense for too long. Yield, if you Google it, if you Google it, it means a transition from elastic to the best rigorous word would be non-elastic. But I could also just say from elastic to plastic or to flow. oops, I say flow now. And flow, I want to say it from the beginning, flow, all rheology knows it. They're just not careful enough when to use it. Flow means, I know the challenge of teaching is not knowing exactly where you are in your background. When I say elastic deformation, perhaps that's already something puzzling to you. The best way is, I should bring a few things. A rubber band. If you stretch it, and you find, gee, I have to exert certain force keeping it stretched. And you let go, it comes back, and stretch it. So that's elastic deformation. You have deformed your rubber band because the rubber band becomes elongated. Okay? So that's, you know, I usually, this course is built on an elementary course where stress and strain have already been discussed. We probably can go through it very quickly, or you can get the book and read it, that part. So basically, deformation is about shape changing. That's all you need to know, is shape changing. The shape of your object is changing because you are forcing it to do so. So for example, a rubber band this long, I make it elongated 3 times as much. So that's deformation because it's shape changing. So this shape changing can be elastic, meaning it's recoverable. If I have a rubber band, I stretch, let go, it come back completely to its original length. The non-elastic, or the word I use, irrecoverable deformation, is the one, if I lengthen it when I let go, it will not be able to return to its original length. It could return a little bit or larger amount, but still 20% not return, or whatever percent not return. Then you can start to claim it's not fully elastic, right? And that's, so a generic word would be non-recoverable deformation. And another fancy word may say irreversible deformation. But basically, yielding, if you Google, is about the transition from this elastic deformation to irrecoverable deformation, which in the case of our dear polymer melt liquid, it is flow. If it's not a polymer liquid, but semi-crystalline polymer or glassy polymer, you could still reach that non-recoverable state, where when you let go, you find, poof, nothing comes back. For example, we have this plastic bag. Well, I don't want to break it, but I can draw it, and you can see when I let go, it doesn't return. But it's a solid, so it's satisfying my condition of irreversible, but it's not in a liquid state, so we call it plastic. So there are a few, everything is built on terminology because they give you the definitions, give you the concept. So in any case, yield, now you can see, or you can guess where yield is used often. It's often used for this. In other words, for a piece of material that is inherently solid-like. So this plastic is perfect, right? It's solid-like, but I can deform it, and I find after some point, as I draw more, the force resisting this no longer increase. So that is an indication, gee, something has happened, because initially the force is always proportional to how much you are deforming. So yield is very often used in solid mechanics to indicate when you're no longer in, shall I casually just say, linear response. Typically, linear response is where you associate with elastic deformation. So fine, yield has been used for solid mechanics for centuries. When you have a liquid, Are you allowed to use that concept? That's the question. And I have insisted on being concise and insisted that the yield is perfectly valid concept to describe our viscoelastic liquid. When I say viscoelastic, I probably next time say a little more precisely about how we start to define that. So, so this concept of yield that is used in solid mechanics, very unfamiliar to rheologists. When we start to use it to capture the same idea that your liquid, well, many of you probably don't have the background and indeed should find it quite funny that your liquid, and of course, do you know what you mean by liquid? Perhaps not. That the liquid can be elastically deforming. That's kind of strange term. Well, of course, when we casually say liquid, it just means the following. The best way, or my favorite way to define a liquid is not going ahead doing an X-ray or doing something else to find out if it's a liquid. There is a cheap mechanical way to define it. The most powerful way to define a liquid. Liquid conforms to any shape change. In other words, liquid is incapable of retaining any force. It will keep deforming if it is a liquid under any amount of force. And that's why when you pour liquid in a cup, it conforms to the shape of the cup. If you pour your dear polymer to a cup, it may not immediately conform to the shape of the cup. It may take time. But in the long time limit, at long times, if it conforms to, if it cannot sustain any stress, then we still call that a liquid. And this is why I should next time or soon today speak about viscoelastic liquid. In other words, how a liquid is fine, but we must be more sophisticated about unique properties of certain type of liquids, such as polymers, that exhibit a solid-like property. And only under certain conditions it behaves more like a liquid. So I know this is very familiar for anyone who have taken polymer physics from this department. And I kind of not quite recognizing all your faces. I know Dong there. I know Shichen there. And the rest of you, are you? Which year are you? Second year? Huh? So you have the polymer physics? From me? No. Yeah. So this is where I fear that the most useful part you didn't take. Just joking. Yeah. So the rest of you. Oh, you're polymer engineer. Great. And oh, great. In fact, you know, we have now a single school now, right? I hope I didn't offend you by showing Jana's outline. I'm adamant. I mean, I'm going to insist that if there is any polymer rheology, let it be updated enough. So have you taken polymer rheology, actually? Have you taken polymer rheology, actually? Oh, my goodness. He will be the witness for what's to come, you know, in terms of contrasting. And you're three, I think. You are from, but not in my course. And you two? Not in my course. Oh, okay. So this is very useful to know because it depend. I will have a very precise idea about what to cover briefly and what not to. How am I doing so far, though? Am I understood here? Am I? Do you follow what I have discussed so far? The challenge, as you know, is sometimes you have to. Maybe that's the time you ask questions. Sometimes you just have to bear with the fact that not everyone have identical background, and some, I have to try to reach out to all of you, but you guys may say, Jesus, this is all I know already. So, so let me try to hit the ground. So, but I'm more concerned about something, what I do that is not sufficiently self-contained, meaning that I rely on concepts that you are not familiar with. I hope this recording is successful, but otherwise, you guys, if you find some part not clear, maybe you should have an audio recording of it. But let's assume at least the signal is there, look like. Yeah. Okay. If anything unclear regarding yield, for example, I swear, I mean, you guys, how much yield is discussed in polymer rheology course? I would say 0. There's one place. There's one place you do, which is so-called the two-space catch-up. We call there's something called yield stress material. That's one place you do. In other words, a material that would not quote unquote flow or deform until there's enough stress. Maybe I will, after the course, I really need to ask you guys whether this definition of a strain or definition of stress is something that you can flip a few pages to learn, or I should cover it for you. I probably should get to ask you that after the class. But basically, I know you had a casual answer to me. If you can flip back your notes, just exactly where yield is discussed, in which sense, we have an English word called yield, but in what context it was discussed, introduced, or used in your rheology? Yeah, so that sounds very much like the so-called catch-up kind of situation. Beyond certain stress, it can flow. That's called yield stress material. That is not unrelated. The concept is correct. I will try to remember to say something that I even discussed in the. I don't. So you will have a book either electronically or hard copy. Probably not necessary for you to read any parts anytime during the course. Probably too early to read the introduction because I was trying to group different topics in there, discuss a little bit. I try to, and I wonder even if it's earlier for you to read the preface. But and maybe my student can assure me. But I think even in the preface, it is where I start to. I think that. Let's get to that. I think where I already start to introduce. Let me joke a little bit. Introduce the concept of. I call it. I call it the. Okay, here comes the challenge of finding my pen. I remember starting. Did any of you guys did any of you guys know anything about Jesus or of where is the pen? Here is, but yeah, here it shows. Okay. Here we are. So I had claimed that, that I have a theorem. Okay, I don't know if I have originality on this or not. I never check thousands of papers, but basically I have a theorem about viscoelasticity, which is something we have yet to discuss in detail. But basically, you know what is elastic. I just told you it's reversible, and viscous, which is irreversible processes. And here's what viscoelasticity means. Something like water, you can hardly really call it viscoelastic, just because the molecules are moving too fast. Okay? But anything else, if you can visualize, I know our polymer is like this, and I know you can keep going. Basically, this is your polymer. I will be more careful next time showing what it is. But basically, this if you look at this blue chain, it will move. Okay, this blue chain will move. Let's say every 10 seconds, it moves to here. Okay, fair, right? That's totally fair. All right, so right away, knowing your background, so this is perfect. Right away, I want you to think about if I want to deform this thing, where a test chain, meaning any given chain, will take 10 seconds to move around. But I'm going to do it in a fraction of a second to deform it. And then, of course, this molecule have no chance to move around. Okay? And lo and behold, you may find that your response will be elastic. But if I'm lazy and I'm going to deform very slowly, by the time I lengthen my sample by 10%, I already spent 1 minute. 10%, I already spent 1 minute. Well, in that 10% of lengthening of my sample, my blue molecule has moved around many of its size already, yeah, by definition. So it turns out in that limit, okay, it is not going to be aware that you are deforming to 10% because you have lots of time. However, the first 1 second, of course, of deformation is the time, of course, the molecule hasn't had a chance to move. Yeah, by definition. So that first second, the response will be elastic. Yeah, because it has no chance to move around. I know this requires me to describe that concept you guys had in polymer physics, the rubber elasticity concept, right? So if you have something that's cross-linked, of course, only deformation you see is elastic. So this theorem basically says, whenever you speak about I just demonstrated through this example. Anytime you interrogate your sample within a time scale much smaller than 10 seconds, you will see elastic response. So I'm just trying to tell you that, or in fact, you will start to ask. So you got a viscoelastic material whenever you have one. there are two things that come to your mind right away if it's something viscoelastic. One is what I just showed you. What is the internal time scale of your viscoelastic material? For example, this one is 10 seconds. That's number one. Number two, if you have elasticity, it should right away come to your mind, there must be a structure that gives you the elasticity. And this structure, in this case, is the chain's inability to cross. Inability, uncrossability. Because if they cannot cross, then the way of getting into each other's way is not so different than chemical cross-linking. Okay? So with this, I can tie everything together. You have a viscoelastic material that where the elastic structure, may I use the word, survives for a certain period of time. In this case, it's about 10 seconds. Survives. So anything within that time frame, the material is elastic because that structure survives. Beyond which, it falls apart. And that's why we have a viscous component in there. So, so with this, I hope actually you can read the preface. Please do read the preface because there were a few different, you can read between the lines. There are few things said about, including that the science is not democracy, that kind of comment. And that has a certain background behind it. So in any case, you can see something very profound here now. You got this viscoelastic polymer liquid, such as this melt, where its elastic structure try to reform over time of 10 seconds. Every 10 seconds, it's renewed. It's a new elastic structure. I will bring the issue of yield right now here. This is a time scale of 10 seconds where the chains by diffusion just happily rearrange itself, right? It tries to renew itself because it's a piece of material. You leave it and you're not doing anything. You're not squeezing it to make a bottle. You're not doing anything. So it takes its leisure, it takes its time, and it diffuses every 10 seconds away this distance. What if you subject it to some very fast shape change? The question is not only whether in 10 seconds your elastic structure will rearrange or not, but rather whether your elastic structure can survive my fast shape change. And what do you mean? Or this is the whole 9 yards of the book. What do you mean it survives or not? Well, the only structure, as I casually said, is this uncrossability. And can I force them to lose that constraint between each other? If you do, you're destroying that elastic structure. If you're destroying the structure, isn't that when you stop having elastic response? And isn't that exactly the point of yield? In other words, I can force my polymer liquid to yield because I'm changing my shape on time scale so short that I do treat my liquid as a solid. Okay? Any questions? I know that right now everything sounds very abstract, which is fine, meaning we have all the concrete content that we'll get to there. But I just want to set the stage for a different type of discussion on the topic. And amazingly, we have with us two of us who have enough familiarity with the traditional discussion. And whatever I'm about to speak about emerges only in the last 15 years or so. So no wonder the books I mentioned, all of them, can't quite speak about any, can't speak volume, can't speak a great deal about it because this is why I'm astonished every time, because I'm sometimes speechless on this. I mean, because rheology is supposed to be a very mature subject, because you really supposedly need it for guiding the processing of 100 billion pounds, of several 100 billion pounds each year. For the remaining time, I think perhaps I could, not, instead of leaving you with something really uncomfortable, I could probably indeed, because I'm not going to occupy much time, indeed just define the languages for you so that we can take off next time. Which is, for those of you, I know quite a number of you did not take my polymer physics 2, for example. Which I'm only half joking when I say that you missed the important part of polymer physics. I actually mean it. And it has to do, so maybe we can remedy it in the future. But in general, I really do want to say a couple of words about it for the remaining time we have. Not much, but we have a little bit of time. So I told you the rheology, or what we're dealing with, it's all about deformation. And I said it's all about shape change. And you can see when that is said, it means I don't care about your classical physics you learned in high school. We are talking about a polymer, a sample, who is experiencing zero net force. There's no force on it. No net force on it, I'm so sorry to say. So I'm not talking about throwing a ball that it will, I'm talking about having a shape change. No acceleration. And this thing will sit still. The center mass will not move. No acceleration. Why? Because the way we process our polymer, much of the way we process it only involves shape change. That's why. So we reduce everything, that's 100 billion pounds of polymers processing every different parts, to a problem as simple as shape change in some simple example. So for example, the way I did it, I put a force on the top surface and the bottom surface, and this is known as simple shear. And I could think about a piece where I just do extension, right? That's the tool. And if you want to be precise, you can call it uniaxial extension. So we'll speak about deformation. We'll speak about shape change. And in each case, and a fancier word is called strand. It means the same thing in reality. And in each case, in the first case, this this deformation, for example, I move it to my upper surface. I hold the bottom surface fixed. I move upper surface by a factor of x over a height of h. Then the amount of shape change is x over h. I'm being a little bit speedy because there are people who already know, and the rest of you just need, if anything unclear, go back to the recording and then go back to the book. It's very quick. And in principle, the way we discuss it, so this could be a liquid. So I may even think about that this was being done by moving my top surface with certain speed, right? That's fine. In that case, the calculation is the same, but there's a way to think about how fast you are changing the shape, which is to think about, oh, that means when I move delta x spanning delta t, then over delta t, my shape change is this much. And then that gives me a rate. And that's shear rate. Okay? So all of a sudden, I have indicated for you that if your upper surface is moving with velocity v over a height of h, then you are imposing a so-called rate of deformation that you, as an experimenter, claim you have control. Because you can control your upper speed, plate speed, v. You know your sample is h in thickness, so you know exactly what kind of shear rate you are imposing. I probably should right away indicate to you. You can probably, I don't mean to be condescending or whatever. You can throw away your books, other books, because those books do exactly what I just showed you, but by doing what I did here, a big implicit assumption has been made. What is that? I just so casually made this such a simple definition, introduction of you folks know very well of shear rate. What assumption have I made? I probably should get your two names. Yours? Alexandro, yeah. Dario. Alex, what assumption have you learned in your rheology book? What assumption is made in here? So I haven't talked about stress yet, so which I do want to do, but I'll give you a little time. Think again. Think more. So this is strength we just talked about. Let's talk about stress. Stress, of course, is so-called force per unit area. The reason you divide it by area because you want to be able to compare your results with somebody else's result. Since you don't pre-communicate in the literature, you may start with a sample this thin, he may start with a sample this thick. How do you compare? Well, you can, because obviously for the same condition, I have to use more force because my sample is bigger than what you do, right? So the force is not quite the right way to communicate, but rather force divided by the loading area. So in the case of shear, a couple of words of let me just get the x, y, z. Couple of words about a little teaser about tensor. So we don't use tensor at all, and I show you why we don't. But nevertheless, for those who crave to have tensor concept discussed, here is what it is. There will be a force acting on the top surface, G, acting on the top surface as well as the bottom surface, which is pointing to the right. So there's a vector pointing to the right horizontally. And it's acting on a surface. It's acting on a surface. The way we define surface is we define its orientation of the surface by looking at its norm. So its norm, oops, I thought I changed. Okay, I thought I changed my color. Its norm is in the y direction. Okay, the way it is. I have a horizontal plane just like my book. Right? So you see, to describe this peculiar force, which we can call the shear force, or better yet, shear stress. Why do I say simple? I don't have to say simple shear. It is simple. It is shear. Shear stress is that I have this force that is acting on a surface that's pointing up. And of course, I want to normalize the area, which is this total area. I get a stress. Well, that's just a scalar. But for me, I may wish to remember, oh, my force was pointing to the x direction, acting on a surface whose orientation, whose norm is in the y direction. So all of a sudden, I see, oh, there are just any stress, by definition, involve the information coming from two vectors. One talk about its orientation of the force, the other talk about the orientation of the surface on which the force is exerted. So you necessarily will remember that there are two directionalities involved in the simple shears x and y. But once I specify it is simple shear, then all I need is a scalar, just this quantity itself. And that's why I joke, not only I don't need tensor, I don't even need vector. If I remember what is my definition, what's left is just a scalar. Yeah? So similar things can be developed for extension. So I just want to be sure for you to take notes. All this is on page 4. All of this. And for extension, that I'm not going to talk about, I probably will not talk about unless you ask, is we go to chapter 3. But I probably say too much when I say that won't talk about. Probably talk about later. It will be on page 63 on the extension part. Because for clarity, I only just took a case of shear to discuss until chapter 3, where we talk about the two most common way of make a shape change. One is shear, one is extension. What else you need to know? Stress is defined this way. All you need to know is it has the unit of force per unit area. Force divided by length squared. So when I describe deformation, I have not invoked how I achieve that deformation. In other words, for example, you need to supply enough force for that deformation to take place. And then the stress arises. But the very discussion here, whatever force that results from this, has a big assumption involved. And so, Alex, I wouldn't be surprised you don't know that there is assumption after taking your rheology. Which, by the way, this is why I said I should be we should teach a more updated version of it, because it's absolutely unacceptable. That anyone, by that I mean that anyone teaching rheology in the world, on polymer rheology, let's per se, I mean, let alone if you want to talk about rheology of granular material, okay? Do you know what is a granular material? Sand. Huh? Go back to your kitchen, your salt. Okay, that's granular material. So if you speak about granular material, by the way, granular material, you can claim that is yield stress material. Okay, because the sand, unless you tilt enough angles, gravity act enough, it will not quote unquote flow, right? So that's yield stress material. Sand, for example. In there, of course, you cannot afford not to talk about what I'm trying to point out here. But I'm saying when you teach polymer rheology, it's no longer acceptable for you not to discuss the implicit assumption in this. It's right. Yes, yes. Yes, yes. So the way we do it, not only velocity, see the way I depict it here, this is a strength field. Same, that I assume if my upper plate moved capital X, then at half height, half h, it moved half x, the way I linearize it. And by the same token, I know, thanks for saying that. So the same thing, if you have velocity at the top, then half height is half v, and 1/3 height is 1/3 v. Okay. Why do we do this? I think that's the even more fascinating question. Why do we do, in other words, why we have assumed the velocity field is linear, using your word. In other words, the deformation is homogeneous. In other words, every layer suffers the same. In fact, I speak out the answer. Every layer is undergoing the same amount of shear, same rate of shear. That's what they mean, right? Obviously, the way, I mean, of course, you have lived with subject, so it looks very obvious to you. So every layer is undergoing the same type, same amount, same intensity of shear. So the question is, why? Or ask the reverse question. What if this is not true? So if it's not true, we're out of business, basically. We are, so I know I often run over time. That's my problem. So basically, if it's not true, so there are really two, so I don't want to say this part. So it turns out, obviously, all textbooks show this formula in the bracket here, in the frame here, without discussing the assumption that there is a linear variation of velocity. It is certainly out of convenience we do so. And it is furthermore out of necessity we do so. Because the lack of this is a nightmare. The lack of having this condition means you lose control of what you're doing. it's the end of rheology if this is not true. And this is why it is nasty. And this is also why it's never discussed, because it will mean the end of our mission. And then let me recall the mission is to study study deformation of matter. And when you do this, there were two parts actually to it. If you want to thoroughly do this, of course you want to know the field, the deformation field. And then you want to know the correspondingly how the stress field, stress response is. In traditional rheology, this is prescribed, is given, is assumed to be known a priori. And that's why we have this. I know I'm running out of time, so let me just stop this part. Then. Any questions?